So this is our first example of something having chain rule twice. So you have a function inside of a function inside of another function. So we're going to start just by rewriting this. I'm going to write the sine 6x on the top with an extra set of brackets. And I'm going to put that power of 5 outside like that, because that sine 5, sine to the power of 5, that is the most outside function, although it's a little bit hard to see if I would have written that negative 5 in here. If I would have written that negative 5 in there, it's hard to see that that is the most outside function. So we'll write that minus 5 on the outside like that. Then when we look, we hit our power rule first, looking from the outside. Inside of our power rule is a sine to the 6x. So the next function we'd hit working from the outside would be sine. And then inside the sine function is a 6x. So our chain rule is going to happen 3 times. Every time we do our chain rule, the idea is we do the derivative of our outside function, keep the inside the same, and then multiply by the derivative of the inside function. So it's going to look like this. The first function is that negative 5. That's going to come out in front, giving us a negative 15. This is going to stay the same, and we're going to subtract 1 from the exponent. So that's our first step. Just did the derivative of the outside function, kept the inside the same. Then we're going to multiply by the derivative of the inside function. The inside function is the sine 6x. It has a chain rule as well, because the sine is on the outside and the 6x is on the inside. So if we do the derivative of the outside function first, that will be cos, and keep the 6x the same. And finally, we have to do the derivative of the last inside function, which is a 6x. So we'll have to multiply by 6 in the end. Yes? So yeah, we should be writing f of x and f prime of x. So it's a little bit more complicated because we got a chain rule inside of a chain rule inside of a chain rule. And you could have even longer ones if you wanted. I've got one at the end of the lesson today that would be crazy. Okay. So try this one. This one doesn't have a chain rule within a chain rule. It's not too bad. And how did you do? So the outside function is the power of 3. That comes in front. Here I decided just to keep the notation. You could add those extra brackets and have it tan x in brackets and the squared outside, or you could have the squared in its proper location as it is there. And then the derivative of tan is secant squared. So it's a chain rule, so then we multiply by that afterwards. Well, the d over dx part here is notation to say find the derivative of. This d over dx is a command, find the derivative. So when we write the derivative, we could write dy by dx, because that's the actual answer. But this part right here is telling us take the derivative with respect to x. So next question. Find the equation of a tangent to y equals sine x at the origin. So we're now looking for that equation of the line. We could draw a quick little diagram of what's happening here. Here's our sine graph. It looks like this and continues. We're looking for right at the origin, which is 0, 0, drawing a tangent line. What is the equation of that tangent line? So thinking back about equations of lines, the 2 things that you're going to need to make an equation of a line are point and the slope. It's happening at the origin, so we already know that 0, 0 is on that tangent line. So we have a point already. All we have to do is find the slope. Now the big idea of derivatives is when we find the derivative, we're finding a function of all the slopes possible anywhere along there. So when I find the derivative of sine x, and the derivative of sine x is cos x, that derivative is an equation for all the slopes of all the tangents, no matter where you are. Which one are we looking for in particular? We're looking for the slope when x is 0. So if you plug 0 in to this equation, our slope will be cos of 0, and from your unit circle from last year, you remember that that's equal to 1. Or you kind of remember that that's equal to 1. Or you kind of remember that you should review that, because you're going to need those values again this year. So now that we have our slope, we can write our y equals mx plus b. Now you know your slope is 1. And technically this is one that you could do really quick, because you do know your y-intercept, because it's going to be 0. But if this was one where the point wasn't your y-intercept, how would you solve it? Well, you'd plug in your point. We know that when x is 0, y is 0. And then you could solve for b and get b is equal to 0. Although you could see that naturally because our point was already a y-intercept. So now, what is the equation of our tangent? Y equals 1x, or y equals x, is that equation. Another show that question. Would you like to try it on your own, or do you want to just work through it? Okay, I'll give you guys a couple minutes. I'll give you the first step. See if you're able to start it off correctly with the chain rule. So this is naturally a place that you get stuck in this question. What makes this one tough is, in the end, we have a cos 2x, which is telling us we're probably going to need an identity. And how do we move from where we are right now to that point? Now, a couple of things that can help you with these sort of proof-like questions. The answer itself, what you want it to show it as, often has hints built into it for what to do next. So when I'm looking at that, and I've already underlined the cos 2x, I notice in the front I have a negative 3 cos x. I see I have a negative 3 cos x here. In order to have this as one term with multiplication right there, what I'm going to need to do is have that factored out. So as a next step, because I know I want a negative 3 cos x in the front, I can factor that out and then see what I'm left with. And once I factored it out, what I'm left with is a minus 2 sine squared x plus 1, which is the same as 1 minus 2 sine squared x. Remembering our double angle identities for cos, that's one of our double angle identities for cos. So then you can just replace that set of brackets with cos 2x. But what we did as a strategy is we saw that we needed a negative 3 cos x out in front. So we used that as a hint to tell us we should factor that out. And then we can move forward, and it's more obvious to see the cos 2x in there. So again, these ones that have a power with tan, sine, and cos, you might take the time to rewrite them with that power on the outside like that, just so that our chain rule becomes easier to see. Our most outside function is that power of 4. Then inside of it is the function tan, and inside the tan function is the function 2x. So to do the derivative, the chain rule says, do the derivative of the outside function. Four comes out in front, subtract 1 from the exponent. multiply by the derivative of the inside function. Keep the inside the same. Then multiply by the derivative of the inside function that was inside the inside function, which is just 2. Yes, the derivative of tan is secant squared. So when we were going to the next function that we have to do the derivative of, that's what we would write, and we'd keep the inside the same. Then we do the derivative of the last inside function, which is 2. Now, if you wanted to here at the end rewrite it so that it had you could do that. And your textbook would probably have the 2 out in front. Oh, and there's a 4 out in front. Thank you. So I'd probably multiply, the textbook would have the 2 and the 4 multiplied together to get 8 in front, but that's not hard to do.